Hi guys, it's AC Coder here, and today I'm going to be explaining about stack in C++. So if you think about stack, what do you think of? Might be a stack of trays, stack of donuts, stack of books. Actually, let us first consider the real-life examples of stack. In this case, we're going to try to see a stack of books. For example, these are heavy books, so heavy that you need to carry it one by one. You cannot carry it the whole thing because it's too heavy. So what can you do with this stack? So first of all, you can put a book number X to the stack. You can put a book, let's say book. Let's say we number the books 3, 7, 4, 2, 1. Let's say we put a book number 1 into the stack. Now if we want to take out the book from the stack, we just need to take out this 1. So now the top is now 2. Then we can read the upmost book. Now the upmost book is book number 2. So we can only read book number 2 in the stack, because reading book number 4, book number 3, book number 7 is impossible because the top book is blocking them. And fourth, we can count the number of books in the stack. In this case, there are 1, 2, 3, 4 books in the stack. The subset of number 4 is that we can check if the stack is empty, which is actually the same as checking if the size is equal to 0. Now that we have seen the real-life example of stack, we can see the stack in computer science. So what is stack in computer science? So by definition, stack is a last in first out data structure. What this means is basically the same thing as the normal stack. We only can access the topmost part, which is the element that you put in last. So we can declare a stack by writing stack integer s. You can replace integer with double or string according to your usage. And then s here is the stack name. You can do the following commands. If you want to put a book number X to the stack, you can do s.push X. If you want to take out a book from a stack, you can do s.pop. If you want to read or open the upmost book, it is s.top. This will return the value at the upmost part of the stack. And the fourth, we can count the number of book in the stack by using s.size. And you can also check if the stack is empty by using s.empty. This will return true if the stack is empty and false if the stack is not empty. All of these operations are done in constant time, which means O1. So now let's try a stack simulation. Okay, so let's say we have a stack S and we want to put a book number 3. So now 3 will be at the top of the stack because 3 is the only book. And if we want to read the top, well then the top of the stack is 3. Then if you want to put book number 4, that means 4 will be put above 3. Then if you want to count the number of books, then there will be 1, 2 books. Then if you want to take the top of the book, we can take 4. So now 3 is at the top of the stack. If you want to take the top of the book, which is 3, the stack will be empty. Now if we want to check if the stack is empty or not, then it will return a true, because currently the stack is empty. Okay, so let's implement the simulation just now. So first of all, remember that if we want to use stack, we must include stack in the library, in the header. So actually, you can also just include bits/stdc++.h. It will include stack, iostream, and queue, and lots of other things. I prefer using bits only, so we can actually not write stack here. So I will just write include bits/stdc++.h. Okay, so now we want to make a stack of integers. So let's make one. Stack of integers s. Now, let's say we want to put book number 3. That means let's do s.push 3. Then we want to read the top. That means we want to print s.top. Next, we want to put book number 4. That means we can do s.push 4. Next, we want to count the number of books. That means we can do cout s.size. Next, we can take the top book. That means we can do s.pop. And then we want to take the top book again, s.pop. Then last, we want to check if it is empty or not. So we can cout s.empty end line. Let's compile, and 3, 2, 1. Exactly as our simulation manually. So that's how you implement it in C++. Now let's try solving problems. Now, Evenup solitaire. This problem is taken up from the Open Kattis online judge. You can try this by yourself. Link will be down in the description. And if you're stuck, you can go back and listen to my explanation. Kattis Evenup. Let's say we have a sequence of numbers. In this case, it's 1, 3, 3, 4, 2, 4, 1, 3, 7, 1. What we can do is we can delete 2 consecutive numbers that sums up to be an even number. So for example, we can delete this 3 and this 3 because the sum is 6, or we can delete this 4 and this 2 because the sum is 6, or we can delete this 1 and this 3 because the sum is 4. Now, if we delete, let's say we delete 4 and 2, it will be left with 1, 3, 3, 4, 1, 3, 7, 1. And in this case, 3 and 4 are now consecutive numbers. So the question asks, what is the minimum number of elements left after doing this multiple times? So after this first deletion, you can do another deletion and another deletion until you cannot do a deletion any longer. But then, what is the minimum number left on the sequence? So the first observation is we only need to consider the parity, because we know that odd plus odd is equal to even, and even plus even is equal to even. So what we really need to know is the parity of the number. We don't really need the value of the number itself. We only need the parity. And we can denote odd as 1 and even as 0. So later, if we want to delete consecutive numbers, we need to delete 2 consecutive 1s or 2 consecutive 0s. Actually, we don't really need this when implementing later on, but this will surely simplify the second observation. Okay, so the second observation, the order of deletion does not matter. Why is this the case? Let's see the following example. Let's say you have 0, 0, 1, 1, 1, 0, 0. Remember, the first observation tells us we only need to care about the parity, which is ones and zeros. So let's just consider the sequence of ones and zeros. So in here there are 0, 0, 1, 1, 1, 0, and 0. So let's see. What if we delete this first before this one? Would it just be the same as deleting this one, then this one? Then the answer is yes, of course, because if you delete this one first, at some point later on you're going to be deleting this one anyway, because they are independent cases and they do not affect each other. Now, let's see how about if they clash. For example, for 1, 1 and 1, 1 here. Which one should we choose? Well, actually, we don't really need to care, because if we delete the first two ones, it will be left 1. If we delete the second and third one, it will be left 1. And actually, it's just the same, right? So that proves that the order of deletion does not matter. So what we can actually do is to delete it from left to right. So let's try doing that. So if we have 1, we cannot delete 1 by itself, so we continue. 3, we can delete 3 with the one previously, because 3 and 1 are consecutive numbers and they sum up to 4, which is even, so we can delete this. And 3 and 4 are consecutive numbers, but they do not sum up to an even number, so we cannot delete this. We continue. 2 and 4 are consecutive numbers and we can delete them. We continue. Now 4, previously we still have a 3 that isn't deleted yet, and now 3 and 4 are consecutive numbers because we have deleted 4 and 2. So now we should check if 3 and 4 can be deleted, and in fact they cannot be deleted. So we continue on. 1 cannot be deleted with 4. 3 can be deleted with 1. So we're gonna delete them. 7 cannot be deleted with 4. 1 can be deleted with 7. So we are left with 3 and 4. So the answer will be 2. Okay, so as you see, we need to have access to the previous undeleted number. So how can we do that? We need an access to the previous element. That is similar to the stack that we have just learned, right? So we can actually just use a stack in this case. So how can we use the stack? So first of all, we can, if the stack is empty, we can put the number in the stack. Next, if the current number and the top of the stack sums up to be even, you can delete them because they are surely going to be consecutive. The top and the current will be consecutive, and if it is even, you can delete them. In this case, 3 and 1 is even, so you can delete them. Next is 3. Now 1 is already gone, so now the S is empty. 3, since the stack is empty, you must put in 3. 4 you cannot pair with 3 because they sum up to an odd number, so you must put it above 3. Now 2, we should check with the top of the stack, which is now 4. 2 and 4 are now a consecutive pair that sums up to be even, so you can delete 2 and 4 in fact. Now we just need to take out 4. Now 4, we need to check with 3 because now 4 and 3 are consecutive, but 4 and 3 sum up to an odd number, so you cannot pair them. Now 1, 1 and 4, you cannot pair them. 3 and 1, you can delete them. 7 you cannot pair with 4, you must put it at the top of the stack. And 1, you can delete 7 and 1, so you just delete them. Now, the remaining ones in the stack cannot be deleted any longer. So, of course, we can conclude that the answer will be the size of the stack after doing the simulation. In this case, it's 2. So let's try implementing this in C++. So first of all, let's see the problem format. Okay, the first input is n, and n input follows. So we need to make an integer n. We need to insert n and do a loop from 1 until n, because it's gonna occur n times. Now, we need a stack, so we're gonna define a stack S, for example. Now, we are going to need a variable, in this case it's integer current, to put in what is the current value. Now, we have known if the stack is empty, you need to push the number. If it's not empty, there are 2 cases, which is if the top is plus the current is divisible by 2, you can do this by modulo 2 is equal to 0. That means you can take the top out of the stack. Else, you need to put in the new current into the stack. After you have done all the simulation, what you need is the final size of the stack. So you need to see out s.size. Let's compile and let's try the following input. Okay, it's correct. The answer should be 2. Let's try submitting to the online judge, and it is correct. So that's how you can implement stack in C++. Thanks for watching. If you like this video, don't forget to like and subscribe, and I'll see you guys in my next video.